Thank you everybody for sticking around on a Friday afternoon. I really appreciate it. So this talk is No Way Jose, but before I start my talk, who knows what Jose is? Awesome. Who knows what JSON Web Tokens are? A few more hands. Well, JSON Web Tokens are a part of the Jose standard, and Jose stands for JSON Object Signing and Encryption, which basically helps us do a bit of cryptography on the web. And that's what I want to be talking about today. I'm going to take you to the basics of cryptography, hashing, signing, encryption, and then we'll see what the Jose standard is and some of the other standards that are comprised inside of the Jose standard, like JSON Web Tokens and some other things. But before I get started, hello everybody, my name is Bellen. I'm a developer, advocate, engineer, and we had to slap engineer behind my title because otherwise nobody believed that I actually can write code. At Alt0, and Alt0 is just an identity as a service provider, which means that we try to make it as easy as possible for everybody to implement a secure authentication flow. So you can basically just focus on building your actual applications. Like introduce, I'm a Google developer expert, and you can find me on the internet as Sam Beagle. Cool. I am a developer. I write a lot of JavaScript, so it only makes sense to me that I'm npm installable. If you want to find my social links or links to this presentation and other slides, just run npx@sambeagle/about me, and you'll find all my links to all my profiles. The links or the slides, if you want to follow along on your phone or see them later, are available at jose.sambeagle.tech, and I'll tweet them later as well, so you don't have to write this down at the moment. And I have to start with a disclaimer, because we're talking about cryptography. I might simplify certain things in order to try to explain them in an easier way. You will not be a cryptography expert when you leave this room, neither will I, because it's a very deep, very complicated subject, but I will try to explain the basics as easy as possible. Also, if you have to do something cryptography related, and the most difficult part about cryptography is pronouncing the word cryptography, don't reinvent the wheel, use and services when doing something cryptographic, because they've been known, they've been proven, they've been created by experts in the field. Cool. In summary, we're going to see hashing and keyed hashing, signing, encryption, and then the Jose standard, No Way Jose. So let's look at hashing first. A hashing algorithm is a mathematical algorithm that maps data of an arbitrary size to a bit string of a fixed size. That's a lot of fancy words for saying whatever you put into a hashing algorithm, the output is always going to be the same size, the same length, depending on which hashing algorithm you use. So if you put in 1 word, 10 words, a whole book, the output is always going to be the same size. The initial data is often called the message, and the outcome is usually called the hash, or sometimes also the message digest. So if I talk about a hash or a message digest, that's the output of a hashing algorithm. And it's a one-way function, which means you cannot take the hash and run it to another algorithm to get back to the initial input. Once you've run something through a hashing algorithm, you cannot reverse it. So it's a one-way function. So if we look at a little example, we have a hashing algorithm, SHA-256 in this example. We have 3 inputs, dog, doggo, and the quick brown fox jumps over the lazy dog. They all have a different length, but the output is always going to be the same length, 256 bits. And this is what a hashing algorithm does. It's a one-way function, takes any arbitrary size as input, and you will get the same output over and over again, the same length output. Some of these hashing algorithms are MD5. If you've been on the internet for quite a while, you might have used this in the past to store passwords. We don't use it for passwords anymore, but there's other use cases where you can still use it for. And then you have the SHA and some other algorithms for hashing as well. So we've seen hashing. Hashing is a one-way function, same length output always, all the time. There's also a variant, which is a keyed hashing algorithm. And keyed hashes lets you validate the integrity and authenticity of the content of the hash, which basically means that you can verify that nobody has tried to tamper with the hash. And in order to compute a keyed hash, you need a key, a secret key. Let's call it a password. So if you have the same example as before, dog, doggo, and the quick brown fox, yada yada, and you put it into a keyed hashing algorithm, HMAC SHA-256, so it's SHA-256, which you had previously, prefixed by HMAC, and you enter a secret key, you get again a fixed size output, because it's still a hashing algorithm, but depending on the secret you add to this algorithm, the output will be different. So if you don't know the right secret, you will not be able to get the output you expect from a hashing algorithm. For example, if you use a right secret, we get a certain hash. If you use a wrong secret, you get a wrong hash. And if you know which hash to expect, you know that somebody has entered the right secret or the wrong secret. So that means that you can validate the authenticity of the hash if you know the right secret. Inside, it looks a bit more complicated. You have a few keys, and you use the inner key together with the secret key to create an outer key, and you use that outer key for the actual message digest. But what you have to remember is you have input, fixed output, and with the key, you can validate the authenticity. And some of these algorithms are HMAX, SHA-256, 384, and 512. There's a bunch of others, but these are the most common ones. And HMAX stands for Keyed Hash Message Authentication Code. SHA stands for Security Hash Algorithms, and 256 bits is the length of the output you will get. So these letters actually do mean something. It's not that somebody just types random letters to create an algorithm. They usually stand for certain things. And keyed hashes are often used to store passwords. We've seen in the previous talk that a password should be long if you want to make it secure. Well, if you have a long and secure password, you also need to be able to store it in a secure way. A keyed hash is one of the ways that you can store it in a more or less secure way. And when storing passwords, they are usually salted before they're hashed, just because if you store them, you add salt is a random piece of data that you add to the password, just so you cannot use rainbow tables, for example. And this has the benefit of similar passwords not having the same hash, making rainbow tables useless. Because if you can imagine, if you enter your password, password1234, and your colleague has the same password, password34, your hashes will be the same. So by looking at the hashes, I know that both of you have the same password, even though I don't know what your password is, because a hashing function is a one-way function. But I can still see you both have the same hashes, so I can know that both of you have the same password. And if I then figure out one of your passwords, I also know the password of the other. So if we prefix our passwords with a salt, a randomish data, your password will be 12, password 1234, and yours will be 34, password 1234. We will get two different hashes. So even if I figure out your password, I still don't know your password because your hashes will not be the same, so I cannot know that your passwords are the same. Does that make sense? It's a lot of fancy words, but a hash is basically something that allows you to store passwords in an even more secure way. And this is how it looks together with the input. You add a random salt, a random data, to the keyed hashing algorithm, and you get your output as previously mentioned. Cool. Hashing, keyed hashing. Let's move on to the next step in cryptography, signing. And digital signatures offer all properties of keyed hashes, so everything that a keyed hash can do, validating the authenticity of the hash, a signature can also do. Plus, it has something that is called cryptographic non-repudiation, which are very, very fancy words. And if you look it up in Wikipedia, you get other fancy words. So on Wikipedia, it says non-repudiation refers to a situation where a statement's author cannot successfully dispute its authorship or the validity of an associated contract. Which basically boils down to cryptographic non-repudiation can prove who created the signature. So you will always be able to tell who has created the signature based on certain things. For example, if you use a check to buy a car, you pay the car dealer with a check, you sign that check with your signature. It's old school technology, but some people still use it. And the car dealerships goes to the bank and just says, here's a check signed by Mr. here in the front row, Thomas. And he said that he was going to pay this car of 20,000 Swiss francs with this check. And the bank says, oh, but Thomas doesn't have the money. The car dealership will be able to prove that you, Thomas, gave that check to him, so you promised to come to buy that car because that check has been signed with your signature. That's basically the same thing that happens with signatures in cryptography. You'll always be able to prove who has created the signature based on certain attributes. And cryptographic non-repudiation enables other parties than the signer to check the signature's validity. So everybody who wants to check the validity of a signature should be able to check if the signature is valid. Digital signatures use public key cryptography or asymmetric cryptography, which basically means that you have a public key and a private key, and you use them to create a signature and to validate a signature. So the signer, the person that wants to create or sign something, that wants to create a signature, creates a signature using the private key. We'll have to remember that we use a private key to create the signature, and we'll use the public key or anybody who wants to verify the signature can use a public key to verify the signature. Now, a private key is something that you keep secure to yourself. It's private. A public key is something you can share with third parties because it only contains public data and will allow other third parties to check your signature. A signing algorithm is usually a collection of 3 algorithms. So if we talk about a signing algorithm, we're actually talking about 3 things: something that generates the public and private key pair, a signing algorithm, and a verifying algorithm. So if we want to create a signature of our input, the quick brown fox, we'll use a signing algorithm, RSA in this case, add the private key, and we get a signature. Now, if we want to validate that signature, we can use the verifying algorithm, pass along the signature together with the public key, and we should be able to get it back to the input and validate that it's the same input that we expect. So a signature can be validated. The hashing function is a one-way function. But signatures are also usually hashed. To make it more complicated, so what you usually do is you first hash and then you create your signature based on the hash, but that's just some extra information. So some signing algorithms, the most commonly used ones are RSA, elliptic curve, and Edwards curve octet key pair. That's very difficult to say as well. There's a lot of difficult words in this presentation that I struggle with, especially since English is not my native language. But RSA keys, some of the more famous algorithms are RS and PS, and then the bit length of their signatures or of their keys. And they're very fast to verify because they're relatively easy. They're CPU friendly because they're relatively easy to compute, and they have good support, especially RS. It's been around for a long time, so people and libraries know how to use RSA keys. But the downside is they require longer keys with a minimum of 2056-bit recommended to be secure, which means that you also get longer signatures because you have a longer bit. While elliptic curves, usually ES256 and so forth, they have shorter keys for the same amount of strength as an RSA key. So you have shorter keys, which means you have shorter signatures, but they're a bit more complex, so they're slower to verify. And then you have Edwards curve octet key pair, which basically is the best of both worlds. They have better signing performance, but they're relatively new, so not every library out there might have support for them, even though they're all catching on, and it's quite normal for these days to find support for these Edwards curve octet keys as well. Okay, hashing, signatures, and encryption. I'm only touching the basics. If you want to go deep, we can talk about it with a beer later. But let's look at the last part of cryptography, encryption. And when encrypting data, we cannot only ensure its integrity and authenticity, like with a keyed hash or like with a signature. The data will also stay secret for outsiders, which means that nobody will be able to read an encrypted message other than the intended receiving party of that encrypted message. And you either need a private key, a secret key, or a password to read the data. It depends on which algorithm you're using. An encrypted message is often called a cipher. If we talk about a cipher, it's the output of an encryption algorithm. There's 2 kinds of encryption, symmetric encryption and asymmetric encryption. And the first one, symmetric encryption, for example, is what's being used on file system encryption, Wi-Fi protected access, WPA password, database encryption. Anytime you're dealing with large volumes of input data that needs to be encrypted, you're usually using a symmetric algorithm because they're faster to compute. So if you have to compute a lot of data, encrypt a lot of data, usually you use a symmetric algorithm. And some of these are the ones listed below, direct IES, for example. And how this works is you have a shared secret, both encryption and decryption. So you take your input, you run it through the algorithm, the encryption algorithm together with your shared secret, and you get your message digest, or you get your cipher, sorry. And then if you want to decode it, if you want to decrypt the message, you will use the same shared secret together with the decryption algorithm to get back to the original message. So you should communicate that shared secret to the intended receiver of your encrypted message. Well, asymmetric encryption works more or less the same, but instead of using one shared secret for both encryption and decryption, you're going to use a public key and a private key, and one will be able to do one thing and the other the other. So the sender asks for the receiver's public key, and we've seen before that a public key is something that you can share with everybody because it's a public key, and you can use that public key to encrypt the message you want to encrypt, and then send the encrypted message to the receiver. and the receiver has access to their own matching private key. It's something you keep secure, and using the private key, you'll be able to decrypt the message and read the original message. So if we look at the same example, you have the input, you run it through the encryption algorithm using the public key, you get your cipher, and then if you want to decrypt it, you use your private key to get back to the original encrypted message or the original decrypted message. And some asymmetrical encryption use cases are TLS, VPN, and SSH. I think we've heard these acronyms before, or at least one of them. Some of the algorithms are RES, RSA, OAP, and so forth. And symmetric algorithms are faster than asymmetrical ones. I've talked about this before. Usually we use these symmetrical ones for bigger, larger amounts of data. And if we have smaller amounts of data, we use asymmetrical ones because they're a bit more secure, since you don't use the same secret to encrypt and decrypt. A detailed example. So let's look at a detailed example because it's all still a bit abstract. You use keys, public keys, private keys, you run them through algorithms, but what does it actually do under the hood? So let's look at RSA. RSA is an algorithm that you can use for signing and for encryption. It's an algorithm that creates a public and private key pair and lets you use those private and public keys to do things. And the first thing you need to do is generate the public and private key pair. A small note, cryptography is usually based on some algorithms using very, very large prime numbers. RSA is no exception. So is 1 million a large number? Is 1 billion a large number? No, this is a large number, where this is 1 million, and this is 1 billion, and I don't even know how to pronounce the actual number. But you're dealing with numbers which have 150, 300 digits easily, and they're all prime numbers, so they're quite hard to compute, which also means that it's quite hard to crack encryption or signatures. That's why they're so secure. We had a question with the previous speaker if quantum computing would make it easier to crack passwords. The answer is yes, but the other answer is by then, hopefully we'll also have quantum algorithms that will make it as difficult for quantum computers to crack signatures and or encryption. So let's look at how we create a public and private key pair. The first thing we do is we create 2 random large prime numbers. We create them in memory, we don't store them anywhere, we just create them because we're going to use them to create some other numbers. So prime number 1 and prime number 2, I have 61 and 53, which are very small numbers, because if I would put very big numbers on screen, that would not be as easy to read. But we generate 2 prime numbers, and we use that to create the lambda as well. So the lambda is the third number that we generate based on those 2 random prime numbers. We keep those numbers in memory, and we use them to generate the public and private key pair. Now, the public key will have the modulus, which is the first prime number times the second prime number, and the public exponent, the coprime of that lambda we created earlier. And the private key will also create that modulus, but instead of a public exponent, it will create a private exponent, which is also some math related to that lambda number we created in the top. And what this means is that the public key and the private key pair, they're mathematically linked to those 2 prime numbers and to that lambda we created initially. Now, once we've created those 2 keys, we can forget about the 2 prime numbers, we can forget about the lambda. The only information we need to encrypt and decrypt, or to sign and verify, is in that private key and public key. So what you'll take away from the slide is that we create those prime numbers, and the keys are mathematically linked because of the RSA algorithm, and every other algorithm out there has some different mathematical function. So, using a public key to encrypt, you have the input, 1, 2, 3, 4. We're going to use numbers because we're dealing with numbers in these algorithms, but usually you have some other input. So 1, 2, 3, 4, if you run it through this function, which is the RSA, the encryption algorithm, and we use the public exponent, 33, and the public exponent, and the modulus, n is modulus, and e is the public exponent. If we use those 2 numbers, which we can find in our public key, and we add them to the equation, we get the output of 2183. Usually you have some data conversion, but at the heart of every encryption and decryption algorithm is still that mathematical algorithm based on which algorithm you choose. So if you then want to use your private key to decrypt, you're going to take that output of your encryption, which was 2183, run it through the encryption algorithm, which is going to take some information from your private key, the modulus, and the private exponent, and if you run it through the same algorithm, you'll see that we get back to the first input, the 1, 2, 3, 4. So because these numbers, these 2 the private key and public key are mathematically linked, we can use some math to do some conversions between public and private and encrypted and decrypted messages. Again, usually you do some data conversion, but at the heart of every encryption and decryption is always that mathematical algorithm, in this case RSA. I created a little GitHub, a little CLI tool that will do the same thing for you. And if you see in an actual example, you have very big numbers where the first two prime numbers are more than 150 digits, for example. But to simplify, it also works with very small prime numbers, but it's very easy to compute small numbers. That's why we use very, very large prime numbers. And if you want to look at them, they're available on my GitHub with a few different branches for large numbers, small numbers, data conversion, and so forth. Okay, I've rambled on about hashing, keyed hashing, signing, and encryption to get to the actual point of this presentation, which I still have 8 minutes for, which is JOSE, JSON Object Signing and Encryption. And it's basically a framework, a standard that hosts a bunch of different smaller things. But first up, why JSON? Well, JSON format is used for serializing and transmitting structured data over a network connection, which means JSON is used on the internet by everybody. And it has excellent support in most programming languages. It came from JavaScript, but most modern programming languages have either a library or core support for JSON, so we know how to use JSON in most languages out there. So all of these things inside of the JOSE standard are going to be JW. Some things, JWT, JSON Web Tokens, but let's start with JSON Web Keys. A JSON Web Key is basically a public key in the form of JSON which you can use on the internet. And this is an example of a JSON Web Key. It's a bunch of JSON. I think we've all seen JSON before. So you have key value pairs, and this can be nested key value pairs in arrays or objects. But we should note is that in this public key pair, there's the modulus and the public exponent, which we saw previously when we looked at the RSA example. So those two things are in there together with some other information about the algorithm that you can use to actually use this private key pair. So this is a public key in the form of JSON, a JSON Web Key. Next up, a JSON Web Signature. It's usually in the form of a string, which is 3 parts added together with a dot, where the first part is the base 64 of the header, the second part is the base 64 of the payload, and the last part is the actual signature, which might look something like this, where the first part is the JOSE header. And if you base 64 decode that first part, it will just give you some JSON, and it tells you, I have used this algorithm to create the signature. The payload is the actual signed content, the content you want to verify based on a signature. Again, base 64 encoded JSON. So if you decode it, in this example, it's foobar. Hopefully, it's a bit more useful JSON for you. But it's always JSON that's going to be in the payload. And lastly, the signature is going to take the header, the payload, run it to a signing algorithm together with either a private key or a shared secret, and you get the signature, which means that if something changes in the header or in the payload, you'll also get a other signature, which means you can use that signature to verify the payload most of the time. You sometimes also want to verify the header, but most of the time you want to verify the payload. So in this example, you take the HMAC SHA-256, which is a keyed hashing algorithm, and run the header and payload together with a secret. If this was a signing algorithm, this would be the... Is the mic out? This would be the... can you hear me? Yes. Okay, cool. Oh, it's... There you go. Anyway, encryption signature is created based on and the payload. If I stay like this, it's better. JSON Web Keys, JSON Web Encryption. Of course, we also have JSON Web Keys, JSON Web Signatures. We also have JSON Web Encryption, which is a very long string, which consists out of 5 parts with a dot in the middle. Where we see again, we have a header, we have an encrypted key, an initialization vector, a ciphertext, and an authentication tag, which is a lot of different words, a lot of special words which have to deal with encryption. Yeah.
This is all live, people. This is what you get.
I prefer to sit in my own house in front of my computer.
Me too.
No, it's a lie.
Well, let's try.
Let's try. Okay. I'll try to stay as still as possible. But JSON Web Encryption, JWEs, use two kinds of encryption. They use an asymmetrical and a symmetrical one, and we'll see why that is. So you have a content encryption key, which is usually encrypted with an asymmetrical algorithm, which is an algorithm that uses a private and a public key pair. And we have, which is the second part of that string, and we have the cipher, the actually encrypted part of this JWE, which is encrypted with a symmetrical content encryption key, the CA key, because the cipher can be, the input of the cipher can be quite big, so we use a symmetrical one for that, which is the fourth part of this string you usually see. So the Jose header tells you a bit of information about the algorithms, both for the asymmetrical one and the symmetrical one, and also the key ID, which key to use. So the first thing you need to do is decrypt the content encryption key, which is the actual encryption key that we use to decrypt the actual encrypted message. So we'll take the second part and check in the header which algorithm we need to use and run that second part together with the private key you own through that algorithm, and you get your content encryption key. And then you can use that content encryption key to actually decode the thing you want to decode, which is the fourth part, the ciphertext. So you check in the header again which algorithm you want to use. Then you pass along your cipher, your content encryption key, which we decrypted in the previous step, together with the initialization vector, which is the third part, which sometimes is empty, and the authentication tag, which is the fourth part. You don't have to know what all of these means, just know that you use all of these different parts together with these decryption algorithms. And you get your actually decrypted message. So your content encryption key is asymmetrically encrypted, and the content itself, the cipher, is symmetrically encrypted with a JSON Web encryption thingy. So both JSON Web signatures and JSON Web encryption keys can be serialized compact as a string, where JSON Web signature would have three parts: the header, the payload, and the signature. And the JSON WE, the JWE, the JSON Web Encryption thingy, has 5 parts. But they can also be serialized as JSON, where this is a JSON Web signature, and you'll see that it has the same information: the header, the signature, and the payload. And this is a JSON Web Encryption thingy, where it has the same information that it has in that serialized as a string thingy, so the protected and unprotected parts, the initialization vector, ciphertext, and the authentication tag. Now, why would you choose one over the other? Well, the serialized as a string are much shorter. So for example, if you use a JSON Web signature and you have to send it over the web, it's shorter to send it as a serialized string than to send it as a bit of JSON. But whatever you choose, it's up to you. Lastly, JSON Web Tokens, which some of you already heard about. A JSON Web Token can either be a JSON Web signature or a JSON Web Encryption thingy, depends on you choose. 99.99999% of the time, it's a JWS. So 3 parts, serialized as a string, because you usually send a JSON Web Token as an access token with each request, so you want to keep it as short as possible. That's why it's JWS, serialized as a string. That's going to be used most of the time as a JSON Web Token. A JWS is more commonly used as a JSON Web Token, okay? The JSON Web Token header tells you the same thing, which algorithm to use to verify the signature, together with the type, I'm a JSON Web Token. And a JSON token can be a bunch of different things. Maybe it's an access token you use to access certain APIs, and then it will contain some information in the payload about the API, who issued it, for which user it is, the audiences, which API is supposed to use this, and some other things. If you have an ID token, can also be a JSON Web Token. It has some more information about the identity. We're not going to drill deep into what an access token and ID token is. Know that there's different kinds of JSON Web Tokens or different kind of tokens which you can use as a JSON Web Token. So I went very fast because we have 35 seconds remaining. The summary: hashing compresses and makes it virtually impossible to get to the real data. It's a one-way function, and it always compresses the data to the same length depending on the algorithm. Keyed hashes protect the integrity of the data, so it does everything that a hash does, plus protects the integrity of the data because you have the secret key. Digital signatures allow third parties to verify the validity and origin of data. You can verify who created the signature. And encryption allows only authorized people to read the data. Only if it's encrypted with your public key, you can decrypt it with your private key most of the time, depending on the algorithm. Lastly, Jose is a set of standards based on JSON that helps us with signatures and encryption on the web. Because it's JSON, we know how to use JSON on the web. The slides are at jose.sambigo.tech. If you want to know more JSON Web Tokens, jasonwebtoken.io. We also have a blog post. Thank you very much.
Thank you, and well done on that little technical thingy. All right, so let's check with the questions. Oh, there's one question from Thomas. Many cryptographers passionately dislike the JWT, JWE, blah, blah, standard, e.g. because you can easily use it in an unsafe way. What's your opinion?
I have very strong opinions about JSON Web Tokens. There's a lot of people who don't like it, and there's another standard called Pacedo, which is a rivaling standard of JSON Web Tokens. I personally don't have any problem with JSON Web Tokens if you know how to use them and use them correctly. So the most issues that those people have with JSON Web Tokens are because a lot of people or a lot of libraries don't use them correctly. For example, if you pass an algorithm none in the header, some libraries will not check the signature because it sees, oh, there's an algorithm none, so it doesn't have a signature or the right algorithm, so it will not check the signature. That's not something you should do. So if you use JSON Web Tokens correctly, in my opinion, they're okay to use.
Okay, thanks. Anyone in the audience here have some questions? Maybe I can re-ask my question that I asked before.
Quantum computing.
Yes. Do you have an opinion? The question that I was asking Alon in the last talk was whether with quantum computing we'll have to rethink what safe passwords are. And
Indeed.
Yeah.
So quantum computing, in theory, would make it very easy to do very big, large computations, which means that it would be very easy for a quantum computer to crack encrypted messages, to crack encrypted passwords or hashed passwords or signatures because they're so good at math. So I think that by the time we have real functioning quantum computers for the masses, we will also have to invent quantum algorithms.
One can only hope.
Yes.
All right. Yes, we have a question over there. Let me just run over real quick.
I'm trying not to move too much, otherwise the mic will...
Just a little follow-up, but this means that the current encrypted messages we send will be public in the future?
In theory. We're not in the future, so I cannot say. But what quantum computing means is that it can handle very large computations that we cannot handle with our current computers. So in theory, yes, we'll have to see.
Okay. Any more questions from the audience? Because there are no questions on Slido. Okay, well,
cool.
Perfect. Thank you very much. It was a fantastic talk. Thank you. Big hand.